Hello, I'm Dan Alford with ARC Specialties.
And I'm Dave Hebble, Manager of Technical Services at ARC Specialties.
First, a bit of history on sour gas. All the oil that's left in the earth is so deep that the pressures and temperatures are so high that the threshold for what is considered sour is now below detectable limits. The implication of this is we can no longer have oil touch steel because the H2S in the oil, which is the sour gas, will combine with the iron to form iron sulfide, free hydrogen. Free hydrogen will migrate into the grain boundaries of the steel, and you'll get spontaneous failure under no load. So what we're having to do nowadays is coat all the internal surfaces of valves and pipes that are used in the oil field with Inconel. And what Dave has done is he's worked on ways to improve the efficiency of this process. The implication of this is we need a much greater volume of weld metal deposited, which takes a great deal of time. We need to work on some way to speed this up. Dave, tell us what you're working on.
So about 5 years ago, we set out to increase deposition rates. And it's important that we maintain the same thickness of our weld deposit. So as we deposit more metal, we have to increase our travel speed so that we hold that constant.
What you see here is a split screen with all four of the deposition rates. On the left is 2 pounds per hour, 4 pounds, 6 pounds, and 8 pounds on the right. We've sped up the video by a factor of 5 just so you can see something happening. You see that the pulsing looks a little bit different on all four of them. What is the pulse rate on the low deposition rate, Dave?
We use a peak and background time of 0.2 seconds.
And then you speed that up, you
Right.
shorten that peak and background time as you speed up the welding?
Yes, we're pulsing at 4 times the frequency.
Okay, so what we're trying to achieve is the same number of pulses per linear inch.
Right, so when you look at the ripples on the weld, they all look uniform.
Okay, so what we're trying to show here is for the same machine, all we've done is sped up the RPM, sped up the wire feed speed, and sped up the pulse rate. You made some changes in current and voltage also, or?
Yes, obviously we have to run a higher current, so we're increasing the current, and we'll run a little bit higher voltage as well.
But it's not proportional. It's not. You're not going 4 times
No,
the amperage.
no. And in fact, we only went from 260 amps peak to 320 amps peak
And that's all it took to quadruple the deposition rate.
in the travel speed. And we did bring the background current up a little bit. So running a little higher background current.
So you didn't quadruple the amperage.
No, it's not a proportional number. We probably went up, let's say 20 amps each time we stepped up our travel speed and deposition rate. So if we look at our heat input, amps times volts times 60 divided by inches per minute, when you start doubling, tripling, and quadrupling the denominator, our heat input drops dramatically. For an example, at 2 pounds an hour, we're probably at 19 or 20 kilojoules per inch heat input. When we get up to 8 pounds an hour, 9 to 10 kilojoules per inch.
Faster deposition, lower heat input.
Lower heat input. And so one of the things you have to watch when you do that, these steels are all heat treatable, right? 4130 and F22. So when you look at the heat input, the heat input dropped in half. We doubled or quadrupled our deposition rates, and these typically we're welding on 4130 steel, which is hardenable, and it's a heat treatable steel, and so it's important if I cut my heat input in half. Guess where my hardnesses go in the HAZ?
Up.
They're going to go higher. So your preheat and interpass temperature is very important at the high speeds so that we can maintain acceptable hardness levels in the HAZ. And speaking of hardness levels, NACE. NACE controls the hardness levels in the heat affected zone, or HAZ, that I was talking about. And it's a maximum of a Vickers 10 250. And so we control our preheat, our interpass, and our heat input.
So NACE, the National Association of Corrosion Engineers, you're talking about MRO 175, the weld overlay specification.
Yes, and there are two things I'd like to point out that NACE covers in MRO 175. The hardness, the heat affected zone, or HAZ hardness, adjacent to the weld cannot exceed 250 Vickers 10. And so we control that through our preheat interpass temperature and our heat input. Another part of that spec, there's an FE5 and an FE10, and that relates to the chemistry. And so on an overlay, we take the chemistry 1/8 of an inch above the original surface. And an FE10 means that it's less than 10% iron. And an FE5, there's less than 5% iron. And so when we're welding on a carbon steel material, that means that 1/8 of an inch above it, there's very little dilution. So it's important to control that dilution. In NACE MRO 175, the FE5 specification says that we need to meet 5% iron, 1/8 of an inch above the original surface. This is an actual weld test coupon. Did 6 pounds an hour on one side, 8 pounds an hour on the other. So let's check the chemistry. It has been machined down to our 1/8 of an inch. And so let's check the chemistry to see what we actually have. And we'll go ahead and we'll do just a quick 5-second check and see what our chemistry is. Okay, so we checked our chemistry, and you'll see Fe, or iron, is 1.22. And so we're well below the 5% limit for Fe5.
So to achieve this Fe5, what is the wire chemistry? What's the iron content in this Inconel wire?
The wires that we use today, the iron level's very low. Usually it's 0.5% iron. And so again, at 5%, it's very low dilution in our weld.
So the Fe5, which is measured at 1/8 inch, is that in the first layer, the second layer? How do you achieve these levels?
Okay, what we do is the first layer we put down, we want it just less than 1/8 of an inch. So when you put the second layer on top of it, the 1/8 of an inch is actually in the bottom of that second layer, so that we achieve the very low levels. So if you look at a typical cross section, here's our first layer, and then the second layer. So you can see that the fusion line of the second layer is right below that 1/8 of an inch. So we're actually taking chemistry out of the second layer.
So this is great. You're telling me that we can quadruple a factory's productivity. How do you do it?
Okay, one of the problems you have, especially at the higher currents, how do you start and stop on the edge? You know, in a valve, we have intersecting bores and seat pockets, so we're starting and stopping the weld as we go around. And those edges, we need to build those up so that they can machine them to a nice, clean, sharp edge. Well, if you started at 300 amps on the edge, it's just going to blow it away, isn't it? And so most of the magic is in the program. We ramp up the wire feed, the travel speed, and the amperage. It's all coordinated so that we're ramping it up, and we get to the end of the weld, we ramp it down, and we fill the crater so that we can build up those sharp edges. So the magic is in the machine.
And still maintain your Fe5.
And we can still maintain an Fe5. It's easy to achieve 6-8 pounds an hour on straight bores. The problem is the intersecting bore and the seat pocket of the valve. We're starting and stopping on the edge. And so if we start at our high current, we'll melt the edge away. We'll ruin our chemistry. It won't clean up when we come back to machine it. So we ramp up our travel speed, our wire feed speed, amperage, everything is coordinated so we can build up this edge. We come around, and when we stop, If we just turn the arc off, will it leave a big crater and it won't clean up? And so we stop, we downslope our current and our wire. Again, everything is coordinated so we can build up the edge of the weld so it will clean up when it gets to the machine shop.
So what you presented today is a way to improve productivity not by 10, 20, or 30%, but by 200, 300, or 400% simply by changing parameters.
That is correct. And again, not every part of a valve can be welded at 8 pounds an hour. And so one of the things on our machine, you have 4 fast buttons that pull up 4 different welding schedules. So with the touch of a button, I can weld at 4 different travel speeds, and depending on what part of the valve they're welding. And so when you stop to think about it, if I am doubling or tripling my welding speeds, one machine can do the work of 3 machines and 3 operators. That's not a bad trade-off, is it?
Well, as a machine builder, I don't know if I approve of this.
Yeah, but you know, our economy is a little tough from time to time, and so how do you justify a new machine? That one machine will do the work of 3.
Indeed. Thanks for watching today. If you saw something of interest and you'd like to improve your productivity, call us. I'm Dan Alford.
And I'm Dave Hebble, and we would love to help you improve your productivity. So give us a call, and we can work on it.
At ARC Specialties, we thrive on problems. Send us yours.